All right, so on to the second topic in thermal physics. This is heat and internal energy we're going to talk about today. So first we're going to talk about internal energy, what it is, what it's composed of. It's a really important topic in thermodynamics, and it really relates the macroscopic concept of thermodynamics, so things like temperature, volume, pressure, with the microscopic, which is the movement of particles. So we'll talk about that in a bit. We're also going to talk about how heat is related to this and how the movement of particles relates to heat. Okay, so what is heat? So Heat is a 1995 crime thriller directed by Michael Mann and starring Al Pacino and Robert De Niro. What? Oh, okay, fine. So that's not the Heat we're talking about today. Nor are we discussing the Miami Heat, the most recent National Basketball Association champions. No, we are talking about the heating of objects. So this guy right here, James Prescott Joule, he was one of the pioneers in heat and the science behind heat. Now you might recognize that name, James Prescott Joule. The last name Joule is the unit for energy. And so it's named after him because he did a lot of formative experiments with discovering energy. So he came up with a paper in 1840 with some experiments. It was called the mechanical equivalent of heat. And what did he do in this experiment? Well, he put a metal coil inside a bucket of water, and what he did is he heated that metal coil. And he measured changes in temperature that took place within the water. And what he discovered was that heat was actually a form of energy. So he knew that energy was produced by the electrical coil. And what he found was that some of that energy got transferred to the water, and that caused an increase in the change of temperature. Specifically, he found that the amount of heating, so the change in temperature, was proportional to the square of the current going through that coil. Okay, so he has this bucket of water. I need to make it colorful. So, bucket of water. And he put his coil inside there. Okay, and then he basically measured the temperature of that coil. This is supposed to be a thermometer, somehow. Okay, what he found was that, again, heat was proportional to squared. Now what's interesting about Joule was that he was actually a brewer. So his family had a brewery, and he worked at the brewery. And on his own time, he did these experiments. He was one of the gentleman scholars that was quite common around in the 19th century. And the Joule Brewery is actually still around. So if you want to have some more information about that, you can Google that. But the Joule Brewery, you can still get brews from there. So a bit of a famous connection between that brewery and the development of science. Okay, and so he discovered heat essentially was energy that's transferred from one body to another as a result of a difference in temperature. So the temperature of this, the water, went from very cold, so let's say it was at, let's say it's at 10 degrees Celsius. And it heated up because of this coil, and it heated up to something like 30. So that's real warm. Heats up to 30 degrees Celsius. This is a change in temperature. Okay, and in science, or in physics, that's delta, which is change, and T. So delta T, the change temperature there. That energy transferred is a result of the difference in temperature. So there's a hint of something that's going to be coming up. The energy Okay, heat energy is, whoops, a little sneak preview of what's coming next. Let me erase this. The heat energy is proportional to the change in temperature. So however much the temperature changes, that's how much heat is transferred. Okay, so think of it, if you're confused by the concepts of heat and temperature, think of it like Mr. Burns, the notoriously stingy nuclear power plant owner of the Springfield power plant. So, Mr. Burns basically is very rich. So he has lots of money. It's American, so it's dollar symbols. Okay, he's very rich, he has lots of money. Think of that like the temperature. Okay, so he has a very high temperature, but because he is notoriously stingy, he's not giving any of that away. Okay, so he's not a very charitable man. I think of that like the heat. He doesn't give off a lot of heat. So he has all of this stuff here, but he's not giving a lot of it away. Okay, so what is this stuff that he has? This brings us to kinetic theory. Okay, in kinetic theory, what that essentially says is that there's all these particles, very small particles that are always moving around. Okay, what's interesting about this is we have temperature, which is something we measure macroscopically, as we talked about last day with mercury thermometers and things like that are used to measure temperature. Basically connects the macroscopic properties of this, such as temperature, to the microscopic properties. So very small particles that are moving around. Okay, and that is basically what that is the internal energy. Okay, so I'm going to change the color of this. So internal energy is the total kinetic and potential energy of the molecules in a substance. So A, there's kinetic energy. So they get energy, and these particles are going to move around every which way, just like in the diagram to the left. But we also have potential energy, and the potential energy comes from the forces between these molecules. So they're called the intermolecular forces. I have to go forward. So intermolecular forces, okay? And those are the forces that basically bind these molecules together. Okay? So things like the electric binding force, okay? So they're atoms with electrons flowing around them. So these are electrons. And these electrons basically bind to other atoms. Okay? It's a rough analogy, but that's where this potential energy comes from. And to actually separate these requires work. So you need to put work into these, you need to put energy into this system to pull these molecules apart, and that's what has potential. Okay, so the internal energy is the sum of all of those energies in a substance. Okay, and this is related to the temperature, because the temperature essentially is going to be proportional to the internal energy, because one important point is the temperature. So the temperature of a body is proportional to the kinetic energy of the particles, okay? And that's the average kinetic energy. So this line above it means the average. And this right here means proportional. So temperature is proportional to the average kinetic energy of the molecules in a substance. So the more kinetic energy they have, the higher the temperature they have. Okay? So we're going to talk about this a bit later in the course, but this is just a brief introduction. But the important bits are heat is a transfer of energy, and the internal energy is the sum of the kinetic and the potential energy of that substance. All right, so that's it for heat and internal energy. Next up, we're going to look at the relationship between temperature and heat a bit more closely.